Okay, so good morning or good afternoon, and in this video lecture, we will be covering our phases of matter. So for this lecture, we have a slightly different book. It's named General Organic and Biological Chemistry by Janice Korzinski-Smith. Please take note, if you're going to find this book, there is a very similar book with the same title, which has the principal word in front of it. Principles of General Organic and Biological Chemistry. This is not covered in that book, so please specifically look for the title you could see on the screen. So let's continue. So we have already talked about the various phases of matter in our introduction. So to review, we have our gas, our liquid, and our solids. As their basic properties, gas consists of particles that are far apart and move rapidly and independently from each other. A liquid consists of particles that are much closer together but are somewhat disorganized because they can move about. And finally, solids consist of particles that are very close to each other and are often highly organized. These particles in a solid has little freedom of action, and they are primarily held together by attractive forces. So how is something a solid, a liquid, or a gas? Primarily, there are two factors dictating if a substance would be a solid, a liquid, or a gas. Number one is the degree of kinetic energy of its particles. When we say kinetic energy, how strong or how fast particles of that substance move. And secondly is the interactions between the particles. How strong those particles are attracted to each other will also dictate if something is a solid, liquid, or a gas. So here on the screen, you would see the generalizations between solid, liquid, and gas. For gas, it has no volume and it expands to fill its container. What the volume of the container is, that would be the volume of our gas. In terms of a liquid has its own volume, but it takes the shape of the container. And for our solid, it has both a definite shape and a definite volume. In terms of arrangement of particles, gas are highly disorganized. They rarely stay together, while liquids, they are still far apart. They are still, compared to gases, they are closer to each other. Hence, they are affected by interactions of our particles. And finally, we have our solid. So these are fixed arrangements of very close particles, meaning the particles are held together by very strong bonds. So first, let's talk about gases as a whole. So when we talk about gases, we need to clearly describe what gases are and how they behave. One theory that we use to describe the particles of our gases is our kinetic molecular theory. So the kinetic molecular theory is a fundamental concept and provides a framework for understanding the macroscopic properties of gases based on their motion and interactions of their constituent particles. So here are the factors of our kinetic molecular theory. First, the particles are in constant motion. This means that gas particles never stop and they continuously move until they hit a surface. When they move, they may collide with other gas particles, but we assume that their collision is perfectly elastic. When we say it is perfectly elastic, no energy is lost. Next, they have negligible volume. Their volume primarily comes out from the space that they take. Gases themselves, they are very far apart and they technically have no volume or very little volume. Next, they are not affected by attractive or repulsive forces, primarily because they are so far apart. Next, they have high kinetic energy. The movement of these gas particles are based on their kinetic energy or based on their temperature. They move very fast, hence they have very high kinetic energy. Next, temperature determines their kinetic energy. As temperature increases, their kinetic energy also increases. Next, there is equal distribution of energy, meaning in a container, all gas particles carry the same amount of energy as other gas particles. And next, we have pressure arises from their collisions, meaning once gas particles hits the sides of the container, they apply a force over an area, hence they have pressure. So when we say gas pressure, it occurs when gas particles exert a measurable force on an area. So force over area is equivalent to pressure, and the gas pressure depends on how many collisions of the gas particles hits the container at a certain time. If they hit more frequently, or if more gas particles hit the sides of the container, the pressure increases. We also have a term when we collate all the pressure that all the gases on Earth exert. It's called our atmospheric pressure. So it's the sum of the total gas pressures applied on the surface of the Earth. Okay, when we measure gas pressure or atmospheric pressure, we use a barometer. So here are some common units of pressure you need to be familiar with. We usually use atmosphere at STP or standard units. However, another common unit is our millimeters of mercury, or mmHg, which is 1 atmosphere equals 760 millimeters mercury. We also have our torr, or torricelli. It's equivalent to our millimeters of mercury. And we also have Pascal and pounds per square inch. You often see pounds per square inch in engineering calculations, or in your car, primarily in your tire pressure. So next we have gas laws that relate pressure, volume, and temperature. There are 4 primary variables when we are discussing gases. This is our pressure, volume, temperature, and number of moles. We use these variables, and there are laws that describes the correlation between these variables, and this is our gas laws. So first we have our Boyle's law, which relates pressure and volume. Next we have our Charles law, which relates volume and temperature, and we have our Gay-Lussac's law, which relates pressure and temperature. So for our pressure and volume, we have our Boyle's law. So as the volume increases, there is a decrease in the surface area of the container. So as the volume decreases, the surface area also decreases. What happens is the gas particles are much more squished together, hence there is more collisions occurring. When there is more collisions occurring, the force applied increases, hence the pressure also increases. So our pressure and volume are inversely related. What this means is as pressure increases, the volume decreases, and vice versa. As the volume decreases, the volume also increases. So the inverse relationship of this pressure and volume is known as our Boyle's law, and on the screen you would find our formula. P1 V1 equals P2 V2. Please take note that this law only accounts if there is no change in temperature or no change in the amount of gas, meaning temperature and amount of moles is constant. Next, we have our Charles law. It states that the volume of a gas is directly related to the temperature if there is no change in pressure or in amount of gas. Imagine that your gas has no limits of the container. It is only dictated by the speed and kinetic energy that it has. This means that the more kinetic energy your gas particle has, the farther your gas particle will go. This means as it spreads, the volume also spreads. So as temperature increases, the more kinetic energy your gas particle has, and the larger the volume you would have. We also have Gay-Lussac's law. We don't have it in our slides. For our Gay-Lussac's law, it relates pressure and our temperature. As temperature increases, kinetic energy increases, and the more collisions occur. So as more collisions occur, the pressure also increases. So that is your Gay-Lussac's law. And we also have a combination of the first three laws. This is our combined gas law. Please take note that for our combined gas law, we assume that there is no change in the moles of gas. So these are, on the screen, you would see our combined gas law. Okay, so here are the summaries of our gas laws from our combined gas law. Please take note of the relationships. So for our Boyles, it is directly related, while for our Charles and Gay-Lussac's, they are inversely related. We also have the fourth and the fifth, which is our Avogadro's law. So for Avogadro's law, it simply states that when pressure and temperature are constant, only the number of moles dictates the volume of the gas. If you have more gas particles, the volume also increases. So moles, or number of gas molecules, is directly related to the volume. As moles increase, volume also increases. Next, we have our STP and molar volume. Using Avogadro's law, we can say that two gases will have equal volumes if they have the same number of moles of gas at the same temperature and pressure. So to help us make comparisons between different gases, we have set arbitrary conditions called our STP, standard temperature and standard pressure. This is abbreviated as STP, and these are the parameters for STP: 0 degrees Celsius or 273 Kelvin, 1 atmosphere or 760 millimeters mercury, and 1 mole of gas. So 1 mole of a gas has a volume of 22.4 liters. Okay, so here, provided that you all have 1 mole of a gas, they occupy the same amount of space at standard temperature and pressure. Next, we have a combination of all the previous laws, which take into consideration temperature, pressure, number of moles, and our volume. So all of this can be combined into a single equation called your ideal gas law. So the product of pressure and volume divided by the product of moles and Kelvin, or temperature, is a constant called the universal gas constant and is symbolized by R. So this is our ideal gas law. P stands for pressure in atmospheres, V stands for volume in liters, N is the number of moles of a gas or the number of gas particles, R is your ideal constant with a value of 0.082 liter atmosphere over mole Kelvin, and T is temperature in Kelvin. If you want to convert Celsius into Kelvin, simply add 273 Celsius. Okay. Next, we have Dalton's law of partial pressures. It simply states that if you have two gases combined, the partial pressures of gas 1 and gas 2 would equal to the total pressure. So take for example, in this slide, if you have a gas worth 2 atmospheres combined with a gas with 4 atmospheres, if you combine them together, their total is 6 atmospheres. So Dalton's law of partial pressure states that the sum or the total pressure of a container is based on the partial pressures of the gases present. So before we move on to our liquids, we have our intermolecular forces, because intermolecular forces would affect how liquids and solids behave, because solids and liquids are affected by intermolecular pressure. So unlike gases, the behavior of solids and liquids cannot be described by a set of laws that can be applied regardless of the identity, because liquids and solids are composed of particles that are much closer together, hence the force of attraction exists between them. When we say intermolecular forces, these are attractive forces that exist between our molecules. We have a set of different intermolecular forces. You have your dipole-dipole, London dispersion forces, or our van der Waals forces, and our hydrogen bond. So please take note that the strongest bond here is your hydrogen bond, and the weakest is your dispersion forces. So first is our dipole-dipole interaction. Our dipole-dipole interaction occurs when we have two polar molecules. So our polar molecules have a positive charge and a negative charge, meaning that two polar molecules have two sets of positive charges and two sets of negative charges. What happens in a dipole-dipole interaction is that the positive end of one dipole interacts with the negative end of the next dipole, forming an electrostatic attraction, which simply states positive and negative will attract each other. So this forms your dipole-dipole interaction. Next, you have your London forces or your van der Waals forces. So London dispersion forces are very weak because of the momentary changes in electron density in a molecule. This occurs with non-polar substances, meaning they don't have any positive or negative charge. What happens here is the electrons in the electron clouds randomly move about the structure. And sometimes, by chance, one part of the structure would accumulate in electrons and the other one would be poor of electrons, or they have fewer electrons. This forms a slightly positive and a slightly negative portion of our molecules. And if two adjacent molecules happen to be slightly positive or slightly negatively charged, there would be an electrostatic attraction between them. Now this is considered very weak because those attractive forces tend to break and form very rapidly in a short period of time. It's always present, but the bonds are not always there. They break and form because the electrons move freely in their electron cloud. Please take note that London forces or van der Waals forces only applies for covalent compounds which has no polar or no poles. Next is your hydrogen bond. Hydrogen bonds occur only with hydrogen and very electronegative substances or electronegative elements like your oxygen, nitrogen, and fluorine. So it only occurs when molecules contain H, O, N, and F, and these are the strongest types of intermolecular forces. Why this occurs is because hydrogen, when bonded to those elements, tend to have a positive charge. Take for example OH. OH is a slightly O will have a negative charge and H would have a positive charge. Hence, hydrogen, positively charged, can also interact with negatively charged atoms of different compounds near it. A good example of this is water. Okay, so here's the summary of the different types of intermolecular forces in increasing strength: London, dipole-dipole, and hydrogen. London is exhibited by all molecules. Dipole-dipole only occurs in polar substances, and hydrogen bonding only occurs with molecules which has an OH, NH, or HF bond. Okay. Next, we have our boiling point and melting point. Boiling point is the temperature at which a substance boils, and melting point is when a substance is converted to a liquid. These properties are dictated by the strength of the intermolecular forces of that substance. So take for example, in boiling, energy must be applied to overcome the attractive forces. So if you have a stronger attractive force, you need more energy. If you need more energy, you need more heat, and if you need more heat, you need a higher temperature. The same applies to melting. So a stronger force of attraction between molecules means that more energy must be supplied. So in terms of our intermolecular forces, compounds with London dispersion forces would boil with the least amount of temperature, and compounds that can hydrogen bond would boil at a higher temperature. Take for example, water. Water boils at 100 degrees because of the very strong intermolecular forces between water. Another one is for methane and water. Methane is a largely nonpolar compound and it only exhibits London forces. If you compare the properties of methane and water, water has a very high boiling point of 400, while methane has a boiling point of negative 162 degrees Celsius. The melting point of water is 0, and the melting point of your methane is negative 183. However, if we are comparing two compounds with a similar type of intermolecular force, meaning London-London, dipole-dipole, or hydrogen bond, we now look to the molecular weight of the substance. As you have a if you have a larger molecular weight, the more intermolecular forces are present, hence the stronger the bonds are. Like for example, you have propane and butane. Butane is 4 carbons, while propane is only 3 carbons. Butane would have a higher boiling point and a higher melting point. So larger molecules have stronger forces, hence higher boiling points and melting points. For our liquid state, because liquid molecules are much closer together than gas molecules, many properties of a liquid is determined by the strength of its intermolecular forces. The molecules in the liquid are still much mobile than a solid, hence giving liquids fluidity and giving them no definite shape. Some liquids move fast enough that they can exit the liquid phase altogether and becomes gas molecules. So next we have vapor pressure. So when a liquid is placed in an open container, liquids near the surface would have enough kinetic energy to overcome intermolecular forces to escape the gas phase. This is called your evaporation, and it occurs until all the liquid has become a gas. Take note that vapor pressure is an endothermic process. It means it absorbs heat from the surroundings. This is why when you sweat and the sweat cools off, your body feels cooler. So in a closed container, some liquid molecules evaporate from the surface and enter the gas phase. As more molecules accumulate in the gas phase, some molecules re-enter the liquid in the process of condensation. Condensation is an exothermic process, meaning it gives off heat to the surroundings, opposite our evaporation. Okay. We also have a state called equilibrium. It only occurs in isolated systems or closed systems. At equilibrium, the rate of evaporation and the rate of condensation are equal, meaning there's no net movement of solid to liquid to gas and gas to liquid. Okay. So we have vapor pressure. When we say vapor pressure, it's the pressure exerted by gas molecules in equilibrium at the liquid state. Imagine you have a can of a gas and you put a barometer in it. If you allow the system to equilibrate, you would read a certain amount of pressure. This pressure comes from gas molecules that transitioned from your liquid phase. So the vapor pressure exerted by a particular liquid depends on the identity of the liquid and the temperature. As the temperature is increased, the kinetic energy of the molecules also increase and more molecules escape into the gas phase. Vapor pressure increases with increasing temperature, which is related to our boiling later. So when we say boiling point, the actual definition of boiling point, it is the temperature at which the vapor pressure of a liquid overcomes the atmospheric pressure. So in base sea level computations, it is 760 millimeters mercury. So if you increase the heat of a liquid, you're not actually increasing simply kinetic energy, you're also increasing the vapor pressure of the liquid. And at a certain point, the vapor pressure of the liquid would now surpass the atmospheric pressure, pushing down on the liquid, causing it to evaporate. So at this temperature, example, water turns into gas at 100 degrees Celsius. It means at 100 degrees Celsius, the vapor pressure of water is greater than 760 millimeters mercury. Next, we have vapor pressure and intermolecular forces. So given the intermolecular forces, the lower vapor pressure at a given temperature. So if you have a stronger intermolecular forces, the lower vapor pressure at a given temperature. Okay? So strongly bonded substances would actually be less susceptible to volatilization. Compounds with strong intermolecular forces have a high boiling point and a low vapor pressure at a given temperature. The next property is called your viscosity. Viscosity is your lapot or labnaw. It is a measure of the fluid's resistance to flow. A viscous liquid is one that feels thicker. Compounds with a stronger intermolecular force tend to be more viscous. Take for example, if we compare petroleum with our liquid water, kerosene or gasoline tends to be very less viscous compared to water. Molecular size also matters. That's why oils, which are long chains of carbon and hydrogen bonds, tend to be thicker in movement compared to water. Another measure of our liquid is called your surface tension. It is the measure of the resistance of a liquid to spread out. It occurs because if you have a liquid in the bulk right here, it is attracted by liquids near to it. Okay, meaning the net movement or the net pull on this molecule is equal. However, if you're on the surface, there is nothing pulling the liquid upwards since this is already above the surface. So what happens is there is an imbalance of the pulling of the liquid, causing the surface of a liquid to curve inwards towards the bulk. So that is surface tension, and it could be measured in tension, so force over length. The stronger the intermolecular force, the stronger surface molecules are pulled down towards the interior of the liquid, and the higher the surface tension. Because water has a strong intermolecular hydrogen bonding, the surface tension is actually very high. For our solid state, so when a liquid is cooled, the intermolecular forces are stronger than the kinetic energy of the particles, hence a solid being formed. Solids can either be crystalline or amorphous. So when we say a crystalline solid, it has a regular arrangement of particles, meaning it has a pattern, it has a repeating structure. When we say it is amorphous, it has no regular arrangement and it's mostly random. So we have different types of crystalline solids. We have ionic, molecular, network solid, and metallic solid. When we say ionic solid, it's composed of oppositely charged ions, like for example, sodium chloride, sodium positive, chloride negative. When we say molecular solid, it's composed of individual molecules arranged regularly. So this is a common compound which is not ionic. A network solid is composed of various atoms covalently bonded together, forming sheets or three-dimensional arrays. And for a metallic solid, it is a lattice of metal cations surrounded by a cloud of electrons that move freely, hence giving it a very conductive nature. So this is the nature of our crystalline solids. In contrast to crystalline solids, amorphous solids have no regular arrangement of particles, meaning they have no repeating pattern, and these are usually formed when liquid cools too quickly to allow regular crystalline patterns to form. Examples of this is your rubber, glass, and your plastics, although most of our plastics are actually polymeric in nature. Okay, so some properties of our energy. We have our specific heat. When we say specific heat, it is a physical property that reflects the ability of a substance to absorb heat. Some substances are capable of absorbing a great deal of heat as temperature increases, whereas other substances are not. The specific heat is defined as the amount of calories or joules, this is energy, needed to raise 1 gram of substance temperature by 1 degree Celsius. So this is the formula for your specific heat. So the larger the specific heat of a substance, the less its temperature will change when it absorbs a particular amount of heat energy. Like for example, water has a very high specific heat of 1. This means that you need a lot of heat to increase the temperature of water. And the last part is our energy and our phase changes. So when we are converting a solid to a liquid, it's called melting. Melting is an endothermic process. This means it needs heat to occur. The amount of heat needed for a substance to melt is called your heat of fusion. Heat of fusion is the energy amount of energy needed to melt 1 gram of substance. The opposite, freezing, is when your liquid turns into a solid. This one is an exothermic process because energy is released. For melting and freezing, the amount of energy is the same. Hence, we only have heat of fusion, not heat of freezing. When converting a liquid to a gas, it's called vaporization. Similar to our melting, it also needs energy since it is an endothermic process. So the energy needed to evaporate or vaporize 1 gram of substance is called your heat of vaporization. Opposite that is our condensation. Similar to our freezing, condensation is an exothermic process. So again, between heat of vaporization, there's no heat of condensation since they need the same amount of energy to vaporize and to condense. Occasionally, there are sometimes solids that directly turn into a gas and a gas that directly turns into a solid. A good example of this is your naphthalene for sublimation or our mothballs. These are when your solid directly turns into a gas without passing the liquid state. And for deposition, this is the reverse process. It's when a gas directly turns into a solid. A good example of this is carbon dioxide. If you apply enough temperature and pressure, it directly forms dry ice. It's called dry ice because it's not wet. Okay. So here's the summary of energy and phase changes. Please take note of the type of process, from what phase it moves to another, and what is the energy change. Is it exothermic or is it endothermic? Okay, that would be all for our lecture on the phases of matter. Kindly go back to the slides that I will give in your LMS. Also, I'll try to make a handout for you to review. That would be all. Thank you for listening. Have a pleasant day.